Let's have a brief look at this exercise here, sequence data quality. So now we have just run this FastP and got some output, right? That's the previous video. Let's have a look at this output because the FastP, well, what does it actually do? If we have a look at the shell script here, it takes these two FASTQ files here as input, and then it does some filtering, right? Removing bad sequence or poor sequence. And this is poor based on the quality scores in the FASTQ files, right? It's not really checking if the read is correct or not. How could it, right? But it relies 100% on this quality score. So if the sequencing machine says that this is a bad score or a little bit doubtful about the quality, it will remove it. So that's why we have three output files. So the paired end reads as that survived the filtering. I mean, if there's a read pair input that survives, it will be output here as a read pair again, right? Possibly untouched, right? Nothing changed to it. But in some cases, one of the two reads will be discarded based on this poor quality. And then the other one, the mate that is left without having a pair, is put into this file here. So we would expect that these two output files here are big but slightly smaller than the input. And then a few reads should end up here, not too many, because if very many reads end up here, it means the quality of the input was very poor, so that many reads lost their mate, right? But this will of course vary based on the dataset itself. And here we can see these three files output now, and we can actually look at the size of them right here in terms of megabytes. So we can see that these two are like 100 megabytes, slightly bigger, while this one is only 4. This looks reasonable to me. This looks reasonable. But this was not what we were asked to do here. We should inspect this HTML file because that's also output by this FastP software. So, and since we are now in a web browser running RStudio, we can just click on this with my left mouse button and view in browser, and then it will open here. So that's a really nice feature about running RStudio on Orion, right? Otherwise we could not do this. We cannot inspect this in the terminal window, for instance. So let's have a look. There are some questions here. How many read pairs are there in this data set? Well, how can we see that? I think it's here. Before filtering, total reads. And this is then the total number of reads, not the number of read pairs, because you have to divide this by 2, right? Because there are R1 and R2 reads. So this is all this together. So you have to take this value and divide by 2. It's like almost 1.2 million. So it's like 600,000, a little bit less than 600,000 read pairs. 600,000 read pairs. Yeah. How long are these reads typically? And then we can see the mean length here. Both R1 and R2 reads are 301 base pair on average. I think that in this particular case, all of them are exactly 301, and that's not always the case. There can be some variability. So the mean is a sensible thing to look at, or the median, right? After filtering, we can see they have become a little bit shorter, 1 base shorter on average, and that is because this trimming will not only discard whole reads, but it will also trim off the ends of the reads typically, because as we will see further down, the poor part of a read, the poor quality part of a read, is typically at the end. So it's not very uncommon that reads become a little bit shorter after this processing here. You trim off the poor end. How about the number of reads and length after filtering? Yeah, Yeah, that's what we exactly talked about now. What are the estimated insert size here? Yeah, this is the one, insert size peak, 499. But if we scroll down a little bit, here is actually sort of the histogram of the insert. And now you have to remember, the reed pairs that overlap each other are the only ones we can use for seeing the actual insert size, right? Now we know the reads are 300 bases long. If the fragment that we sequenced was 500 bases long, the two reads will overlap each other. 300 from one end, 300 from the other end, right? That will make an overlap of 100 bases in the middle. So from such reads, we can actually see that the fragment or the insert size, that's the fragment length, right? Is 500 bases. But for the fragments who are longer than 600 bases or 550, because you need certain overlap in order to be sure of this, that they actually, you don't see an overlap if it's too short, right? So in those cases where the fragments are longer than the two reads together, you will not detect the actual length of the fragment. But we can see from the shape of this distribution, if we now assume that this is a normal distribution, we see that we only see the left sort of half of it. And we presume that it will continue up here and then drop back again, right? Like a normal distribution. So we only see like the left part of it. And yeah, so you can see this almost 75% of the reads have an unknown length. They are out here, right? So it's not really half, it's much more than, it's only like a quarter of the read pairs we see here, according to this. But based on this, the software tries to make an estimate of where is the peak, where is the average sort of insert length, and that is what we saw up here, and that was 499. Yeah. So I think this is highly uncertain value when you have only almost 75% of the reads are not really out here somewhere. But that's estimate anyway. 500 bases, you could say. 499. That's quite a good fragment size, I would say. They should be long. They should be long. What is the percentage of reads surviving the filtering? Okay, if we look at the number of reads here and divide by the number of reads, this is after filtering, right? And divide by what we had for, we can see this fraction. But I think it also displays, if you click on this one, yeah, you can see the actual percentages here. Reads past filtering, 97%. What is the main reason for discarding reads here? And this should also be visible here, I think. Reads with low quality, 2%, 2.65, yeah, more than 2.5%. With too many n's, I mean, n's are an n is a base that is so uncertain that we cannot say if it's A, C, G, or T, and then we put an n there, the sequencing machine. Only very few n's here, and too short, none. So this is the main reason, low quality. Sorry. So, were any adapters found and removed? Well, not many, I would say. It says the input has little adapter percentage. Probably it's trimmed before. Yeah, and that's frequently the case, right? Because the sequencing procedure itself will try to trim off the adapters. So the adapters we locate here are only some leftovers, you could say. So very little adapter sequence. You can see there are some occurrences of some of these adapter type of sequences here, but not very much. Yeah, compare the read quality profiles before and after filtering, and then we have to scroll down. Here is the R1 reads before filtering. And notice now the x-axis is logged here. So here we have the first few bases of quality score 33 and something. Then it goes up. This is quite typical. The first bases are a little bit poorer than the next ones. And then we have a good quality score. I mean, the 4 colors here is for ACG, yeah, the different bases. But you can see they are almost the same. There is usually not a big difference between the bases when it comes to quality score. But what we typically see is then after towards the end of the read, the quality drops. But it doesn't drop lower than like 30. So this is excellent quality here. But this is a mean value, right? This is an average across all reads, R1 reads. So there could be plenty of reads who are sort of poor by themselves, right? This is an average. There's a variation around this average. This was the R1 read. If we go, yeah, I skipped this one, to the R2 reads, we see a similar profile, but notice the qualities are lower. It starts out a little bit lower and it drops to much lower. But even here, it's about 20. So I would say in general, it's sort of good quality, but there are, again, this is the average. So there are probably, and if we scroll down to see how it looks like after filtering, I think that the R1 reads are not changed very much. You can see it ends like 30 now. It should be a little bit higher, right? Because we discarded some poor reads, but there wasn't very many poor reads to discard here. So that's why the picture doesn't change very much before and after filtering here. So yeah, if you have good quality reads, filtering is not that effectful, of course. Now you should try to trim off the ends of the reads here, because you can see the poor part are always at the ends, especially this end, right? So that's the next exercise. Try to do that and make some similar plots and see how it changes.